Hello AP, this is Mrs. Sargent, and this is the beginning of Chapter 13, dealing with chemical equilibrium. So, the equilibrium condition, as we have learned with stoichiometry, we've assumed that chemical reactions proceed to completion and that all of the reactants are converted to products. However, there are many chemical reactions that stop short of completion. And we will learn to examine and calculate the progress of these reactions. So some reactions will stop short of completion and some approach completion, but then they reverse. So what is chemical equilibrium? Chemical equilibrium is the state where the concentrations of the products and the reactants remain constant over time. Equilibrium is dynamic, and so particles are constantly forming products, and then they are also reforming reactants. So we have reactions going both forward, left to right, reactants forming products, and then we also have them going in reverse, products forming reactants. So if mostly products are formed, the reaction is said to lie to the right, and if mostly reactants are present, the reaction is said to lie to the left. So here you can see in this graph, we have a forward rate and a reverse rate, and then here is where equilibrium happens when the forward rate is equal to the reverse rate. And so we see that flat line on the graph. In this particular example, the forward rate is very fast and the reverse rate is very slow. You can see this because it's drastically decreasing for the forward rate and then a slowly increase for the reverse rate. And at this point right here, the rates are equal. So equilibrium conditions. Any chemical reaction in a closed vessel will reach equilibrium. The reason why it has to be in a closed vessel is because then there are not outside factors contributing to that. Whereas if you have a beaker that is open to the air, you have the atmosphere and stuff like that that is contributing. At equilibrium, the forward rate is equal to the reverse rate. So draw in the diagrams from the PowerPoint and then graph the progress of the reaction in the graph provided. You may pause the video if you need more time to do your drawings and graphs. So to start with, at the beginning, we have these NO2 particles. And so on our graph, we are going to have NO2. We have 6 NO2 molecules here in our diagram, and then we are wanting to form nitrogen dioxide, or the dimerization of nitrogen dioxide. So in this picture, we don't have any N2O4. So we have 0 down here for N2O4. So this is a typical reaction that's starting with all reactants and no products. In this second diagram, you can see that we have one N2O4 molecule, and then we have all the rest of these are still NO2. So in the second graph, you see a decrease from 6 to 4. I would say this would be at time 1. These numbers should be shifted over. And then for your N2O4, it is increasing by 1. And then here in the third picture, we now have 2 N2O4 molecules, and we have 2 NO2 molecules. So we had gone from 6 to 4, and now we are down to 2 for our NO2. And then for N2O4, we increased to 1, and now we are at 2. And then here in the last picture, we still have 2 of our N2O4 molecules, and we have 2 of our NO2 molecules. So we don't see any change that has happened in the number of molecules. And at this point, you're not going to see any change in concentration. This is the equilibrium, because after this third picture, we don't see any change in the concentrations. Sorry about my dog. She saw somebody walking down the street. If you need to pause the video to finish up your drawings or your graphs, go ahead and do so. Okay, so here's another example. The synthesis of ammonia from its elements. So the reaction is N2 reacts with H2 to form ammonia. And so how much of the product do we start with? Well, according to this graph, we start with no product. We only have reactants that we start with. So we start with no product. Which direction is favored at the beginning of the reaction? Well, if we don't have any product, it can't favor the reverse direction. So it is going to favor the forward direction, or to the right. I feel like most of the time you hear favoring forward and reverse, but right to left is also appropriate. Why does H2 have a steeper curve than N2? Well, if we look at our balanced equation, we have 3 molecules of H2 that are required to react with 1 molecule of N2. So we have more of that reactant, so that's why it's going to be steeper. That reactant, I think is what I said. The balanced equation uses more moles of H2 than N2. At equilibrium, are the amounts of the reactant and the product the same? No, we do not have the same amount of our product in H3 as what we have with either of our reactants. But you can see that we do not have any change. These have all flatlined, and so we have now reached equilibrium. So some key points to take away. Molecules react by colliding. So high concentrations of reactants lead to the formation of products. When product concentrations increase, the reverse reaction is favored. All equilibrium systems are working to increase the entropy. That is delta S is increasing, while decreasing the free energy. So delta G is decreasing, and the final system should have the lowest possible energy. A system will remain at equilibrium unless disturbed. Okay, so I have a video that I would demo this in class, but we're not in class, just to kind of give you a visualization of equilibrium.